Hello students. In previous class we have discussed some basic concepts of complex analysis and which is the continuation of that basic concepts of complex analysis. These are also important points in that, in those which we called it as interior points and boundary points. There are two types of limit points. One is interior points that we call it as inner points, and boundary points. A limit point Z0 of S it is an which is collection of the points in the closed domain, that is an interior point. If in the neighborhood of Z0 there exist entirely the points of S, means what? That is the points which lies inside the closed which is the neighborhood of Z0. So within that closed curve, that we call limit point. And if all the points in the neighborhood of limit point Z0 which do not belongs to S, means this is Z0 is called the boundary point. Means what? That Z0, that is the points in the neighborhood of limit point Z0 which belong to the set. That means what? It does not belong to within that. Means what? It is not the inner points. So which is what? Which we call it as a boundary points. Means what? Which we have that is on the boundary there. That is. So based on that we can we shall define that is open sets and closed sets. A set which consists entirely of the inner points is said to be an open set. Means what? The points which we called it as inner points, means what? Which is inside that domain, that we called it as a open set. The complement of open set is an closed. That is, a closed set is also characterized by saying that a set is closed if and only if every limiting point of the set belongs to the set. Means what? Including the boundary points, that is which we called it as on the boundary, which we called it as, that also includes that boundary points which we called it as a open set. So for example, that all the points which lies inside the circle excluding the boundary there, which we are the interior points or inner points of the set, mod Z is less than R. All the points on the circumference of the circle, mod Z equal to R, are the boundary points. Means what? Keep remember that, so that the points which, if you take a circle, the points which lies inside the circle, which we called it as that set of points, which the set of inner points which we called it as open sets, the set of points which exterior points on, means what? It is on the boundary, which we called it as a closed sets. So that is, we have here example is circle. On the circle which we have that is a closed set including, and within the circle point which we call it as open set. The set mod Z is less than R is an open set because only those limiting points which are inner points belong to that set. But the set mod Z less than or equal to R means what? Closed set is a closed set as the limiting points both inner as well as boundary points, which we call it as a closed set, which belongs to that set. So now let us see that here complex derivative, that before derivative which we have there, that is the closed that is which have that here complex function, as we have know that continuity, that before a function f of z is said to be continuous at z0 if limit of f of z as z approaches to z0 is f of z0 itself. Means what? If you take any function, that function is said to be continuous only if that variable is approaching to that point is equal to the functional value at that point, is which we called it as a continuous. Means what? There is no break at all in that domain. in that function, that we called it as a continuous function. What do you mean by differentiability? How do you define the differentiability? A function f of z is differentiable if limit of f of z plus delta z minus f of z divided by delta z, limit as delta z approaches to 0, which is this limit exists and which is independent of the path along in which delta z approaches to 0. That we called it as a differentiability. Means what? If you want to say that function is differentiable, if the limit exists and which is independent of the path joining along which that delta z approaching to 0, either it is in the real axis or else it is in the imaginary axis, so that whenever that's why it is independent of the path along which delta z approaches to 0. That is, you can define in another way. In the real derivative, dw, w is the complex function of the complex variable z. This dw by dz is f dash of z, that is limit of f of z plus delta z minus f of z divided by delta z as delta z approaches to 0. Where in real analysis, here limit of f of x plus h minus f of x divided by h, that h approaches to 0 or delta x approaches to 0. That is in the real analysis. But in the complex analysis, only variable is complex variable. That's why we can take it here, z here. Now let us see that what do you mean by analytic function. That as we have discussed that, what do you mean by single valued, that if any complex variable in the domain, its image is also in the only one point that we have, that is single valued function, that which is differentiable at point z equal to z0 is said to be analytic function at the point z equal to z0. That we called it as a analytic function. That means what? You keep remember the points that if at all you want to say that analytic function, it has to be, first it has its own limits, it has its continuity, it has its derivative exists there. If at all derivative exists, limit already exists there. If at all limit exists, continuity also exists there. So that all this holds good, then we can say that that function is an analytic function. So that is what we have there. So that just a notation for this here in the complex analysis, z, as you know, that complex variable where x and y are the real number, that can be defined as x plus iy in the Cartesian form, and differentiation of this delta z is delta z equal to delta x plus I delta y, and in the polar form delta z equal to that re to the power of I theta into I theta. Means what? You can use it here, product, then we can write it re to the power of I theta I into delta theta, and with respect to r, that is e power I theta keeping as it is. This is what. And notation for del u by del x or dou u by dou x is ux. That is what we can take it in, that is the limit form of the derivative here, u of x plus delta x, because only approaching with respect to x there, that's why there is no delta y there. That delta y is 0. That is what here. Just notation for this dou u by dou y is u with respect to y, that keeping x constant. So that is, it is a partial derivative, that. So that these are the notations for this one. Now let us see that here, that is very important points, that is derivation here. So in every time, this is in every exam, they might be asked this question. So prove that function, any function should be analytic, that. So that derivation of analytic Cauchy-Riemann derivation of function to be analytic, so that we called it as Cauchy-Riemann equations in Cartesian form or polar form. First, let us prove that Cartesian form of the analytic function. See that this is the theorem there, which we have that Cauchy-Riemann equations in Cartesian form. So one is necessary and sufficient conditions for function to be analytic. First condition is necessary condition that we have here, as we have, that is the necessary condition that a single valued function f of z, u of x comma y, so plus iv of x comma y is analytic at any point z equal to x plus iy, is that there exist four partial derivatives, that as you know that these partial derivatives ux, uy, vx, vy means what, u with respect to x and y, v with respect to x and y partially, and satisfy these equations means what, these relations satisfy dou u by dou x equal to dou v by dou y, or del u by del x equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. Relation between the u and v with respect to x and y, and relation between the u and v with respect to y and x, these which we called it as a Cauchy-Riemann equations. So these are the very important in starting with, that is the complex analysis. If at all you want to say that function is analytic, that function has to satisfy these CR equations. Now let us see that proof of this CR equations. First you take, as we know, the definition of analytic function. If at all that function is analytic, that derivative exists, you take the definition of the derivative. That derivative exists and it is unique, that. And in the Cartesian form you take it, that is z equal to x plus iy, and that x plus iy, and then that you can replace it here in this derivative, and let delta x, delta y and delta z be the increments in x, y and z respectively, that. So just you can replace it here, z replaced by x plus iy and this one, so that as we know that function of f of z is u plus iv, that we can take it in this form in this here, that is f of z plus delta z is u of x plus delta x and y of y plus delta y plus iv of x plus delta x comma y plus delta y. This is what f of z plus delta z. So then it is what f of z is u of x comma y plus iv of x comma y as limit delta z approaching to 0, that is divided by delta z. As we know that delta z is delta x plus delta y, I delta y, that we can replace it later. Just we can splitting the real and imaginary terms in here, so that in the equation 1. Now we have two cases arises here, because if you take it here, as we have like this in the we have a real axis, imaginary axis, as well as another one is which we can take it here as a real axis. We have a, this is u, this is a v there now. Now we have a, let us this along the real axis there. So therein y is 0, as we know that, and ultimately delta y is also becomes a 0 there. Then delta z, it becomes delta x only, as we have that in the previous here, that is here delta z is delta x plus I delta y there, where delta y is 0, then this equation becomes, that is the only delta x here. Then this delta z, it is only that limit approaching delta x approaching to 0, and in which that delta x approaching to 0, these are the definition of, that is the partial derivative of u with respect to x, these are the partial derivative of v with respect to x. This is what we have a derivative, that f dash of z equal to, this is that is along the real axis variation, we have seen that. And wherein that next we can see that we have that is the along the